with a factor analysis. Now remember, I was telling you that once we do this CFA, we will estimate two things, which is once you have the CFA results, okay, once you have the CFA result, we will compute now, because now this model has actually estimated our measurement errors and it has estimated the true factors. It has estimated the true factors. So using the CFA run, we are going to now talk about convergent, discriminant, validities, right? So we are going to talk about these two kinds of validities, and to do that, we are going to compute two numbers. One is called as CR, which is called as composite reliability, and the second one is what we call as AVE, which is called as average variance extracted. Okay. Now, what is composite reliability? Composite reliability is given by the formula. I'm just going to summation. So composite reliability, it is computed for each construct. So let us call it as construct J. It is given by lambda I J, I varying from 1 to k whole square. Okay, whole divided by summation lambda I whole square, I varying from 1 to k plus summation error variances associated with item I varying from 1 to, actually let us call this as kj. Okay. Now let me define what are these terms. Okay, this is this will also be. Now the first factor that we had, let us do it for the first one. EMP had 3 items, right? So J is equal to 1. We are computing the composite reliability for the first latent factor, and we had 3 items, I1, I2, I2. So what is Kj? Kj is number of items for latent factor J. So what will be Kj? Very simple. This latent factor J has 3 items, so Kj becomes, right, because this has. Then this is E1J, E2J, and E3J, and J is 1. And then you have the loadings lambda 1, 1, lambda 2, 1, and lambda 3, 1. And this is E11, E21, and E3. These are our errors. So what will be the composite reliability formula for latent construct 1? It will be, what are we saying? Summation lambda ij for I varying 1 to 3. So what will it be? It will be lambda 1 1 plus lambda 2 1 plus lambda 3 1 whole square. Sum of the loadings whole square. Right? And let me also mention here that lambda ij, they are all standardized standardized loadings. They are all standardized loadings. Now this whole divided by, again the same sum, so it will be lambda 1 1 lambda 2 1 lambda 3 1 whole square plus summation of variance of errors. So variance of E11 is given by 1 minus lambda 1 1. This is the formula. Variance of E21 is given by 1 minus lambda 21 square, and variance of E31 is given as 1 minus lambda 31. So what will it be now? This will be nothing but 1 minus lambda 1 1 square plus 1 minus lambda 2 1 square plus 1 minus lambda 2. So this is the formula for composite reliability for latent factor 1. Then we'll compute the latent for latent factor 2 and latent factor 3. And we say that composite reliability, just like alpha, should be greater than 0.7, which is an indicator of convergent. Remember I told you convergent validities are of two types. One, that our measure that we have developed correlates with another similar measure, that is one kind of convergent validity. And the second is that the items load onto the latent bucket as expected, right? So this CR is telling us that there is convergent validity of the second kind, convergent validity, and the items are loading onto the latent factor, and 0.70 means here that having account. So what is the interpretation of composite reliability? It says that having, now you see in alpha we had no idea of the measurement error. When we were computing alpha, we had no idea for measurement error. So now what are we saying? Having accounted for measurement errors, in the items or let me just call this as the ratio of true variance, that is variance of x true, to variance of x observed, is greater than 70%. That even after I have accounted for measurement error in the items, my items are capturing more than 70% variance in the, and there is, which also means that there is inter item consistency, that the items can explain more than 70% inter item consistency. So this is called as composite reliability. Having accounted for measurement error, I am still proving that there is inter-item consistency of more than 0.7, right? That is, and the variance accounted is more than 0.7. The ratio of x true to x observed. That means x true, the variance of the true variance is more than 70% of the total variance, that is captured by all the items. So the true variance is more than 70%. Then what will this be? It will, if you bring this formula, it will be the true variance is more than 70.70 of the overall observed variance. Right, so there is high inter-item consistency, and the items are good measure of the underlying construct, and therefore we call this as the second kind of, this is a kind of convergence validity check. Okay, now the second computation, the second thing that we are looking at is what we call as average variance extract. Average variance extracted formula of the jth construct is very simple. It is given by lambda I j square. So summation of lambda I j square, I varying from 1 to a j, and whole divided by a. So if I am doing it for my EMP, what will it be? I am going to do lambda 11 square, lambda 21 square plus lambda 31 square whole divided by 3 kj, because kj is 3. Remember, in this we were saying we will sum up the loadings and then square it. Here we are saying we will square the loadings first and then take the sum and divide it by 3. So we will take the average of the squares of the. So average variance extracted. What does average variance extracted mean? What is the definition of that? Means on an average, and we usually test for that the average variance extracted should be more than 50%. So we are saying on an average, the latent factor explains more than 50% variance in the items. It explains more than 50%. That means the latent factor is actually accounting for, on an average, 50% variance in each of these items. And therefore, this is another measure for convergent validity. So when you are doing convergent validity using CFA, you will report two indexes, one CR and you will show that the CR for your sub-dimensions or whatever factors you are working with is greater than 7.70 and the AVE is greater than 0.50. So these are the two convergent validity of items onto latent factor G. Latent factor G, right? Whatever latent factor you are. So this is the thing that we will do for convergent value. Now the second thing that we follow for the second thing that we want to do using the results of CFA is what we call as the discriminant validity test. Discriminant validity test. Now what is the discriminant validity test? Discriminant validity test says that if I have three dimensions here. So I have one and then so I have my three factors F1, F2 and F3. F1 is EMP, let's say this is AX and this is task. Now the discriminant validity test is that I will report, let us write the AVE for the three factors along the diagram. So this is AVE F2 and this is AVE F. And then what I do is, this is the diagram and then I have R, that is correlation of factor 1, factor 2, and this is correlation of factor 1 with factor 3, and then you have the correlation of factor 2 with factor. So these are all correlations. Okay. Above the diagonal, this is the diagonal. Above the diagonal, we take the R square. This is also F1, F2, and F. So we'll take the R squares of the correlation. So it will become R square F1, F2. This will become R square of F1, F3. And this will become R square of F2, F. Now the test for discriminant validity. Okay, so the discriminant validity test that means what are we trying to prove here? We are trying to prove whether F1, F2, F3 are distinct or they have a significant overlap. Whether if these were three dimensions, are they actually, can be said that they are very distinct or there is a significant overlap amongst them. So what is it that we will do? And this can be extended to constructs also. We will do it tomorrow when we will test between the distinction between leadership, PJ, and creativity. So the conditions are, number one, AVE of F1 should be greater than R square F1, F2, comma R square F1, F2. That means the average variance extracted of the items by the latent factor is more than What is R square here? It is actually, this is unique variance explained, unique variance explained by latent factor, whereas R square F1, that means F1 with F2, that means how much is the communality or how much is the shared variance. Similarly, F1, F2. So this is an estimate of the shared variance of F1 with other constructs. So what are we trying to say through this condition? We are trying to say that there is more uniqueness than shared variance. If this condition fails, what are we going to say? That actually this factor has a significant overlap with other factor. That means they are not discriminant. The factor is not discriminant from the other factor, right? So that is one condition. The second condition is ABE for F2 should be greater than R square. Again, it is R square F1 F2 because F2 has a covariance with F1, and R square F2 F3. That means it's shared variance with F1 and shared variance with F2. And the third one is AVE F3 is greater than R square F1 F3 and R square F2. Right, so again there is, if these conditions pass, then the factors have more unique variance than what they share here, right?